Hello, welcome back to this series on trigonometry with college algebra. We're going to continue our review today of the algebra portion, talking about complex numbers, so let's get into it. So we'll start off by talking about the definition of complex numbers. We'll talk about the operations, addition, subtraction, multiplication, and division. We'll talk about the complex conjugate and how we will use that. And we'll finish off by talking about powers of I and how to simplify. So we'll start with the definition here. The imaginary unit I is defined as the square root of -1. Now, it is unfortunate that we refer to this as an imaginary number or an imaginary unit because it definitely exists. It is not just a part of our imagination. It has very real consequences, especially in engineering and lots of other fields. But I believe it came from Descartes, who said, oh, what if we could imagine that we could take the square root of -1? What would happen? And as it turns out, all the rules of math still apply and are still consistent. So we can use that to play around. So that is the imaginary unit. And if you're ever asked to find just the purely imaginary part, that is just the purely imaginary part with the I attached there. But the complex number, or a complex number, is of the form a plus bi, where a and b are real numbers, and we kind of have the real portion of the complex number and the imaginary portion of the complex number. So we'll look at a couple of examples here of just simplifying. So here we've got the square root of -64. Well, the negative is what is a little bit different here. Hopefully we recall that the square root of 64 is 8. So kind of skipping some steps here, we could just kind of get to the punchline that this is 8i. But to maybe use some stuff from previous lectures to help make this make a little bit more sense, what we could do is separate this into -1 times 64. From there, we could use one of the properties that we talked about with our review of radicals, where we could split this apart over the multiplication. And what we've got then is the square root of -1 times the square root of 64. And now I think it's a little bit more straightforward, or a little bit clearer, at least in my eyes, that this does truly simplify to, well, the first portion here is going to be I, the second portion here is the 8, and maybe if we write that in a little bit more of a standard way, we do get 8i as our simplification here. So whether you want to just skip straight to the end or you want to work this out in between and see all the steps is up to you. There is some kind of weirdness going on with splitting it apart. If both of these had negative radicands, we're in a little bit of danger, and there's some mathematical caveats there. But as long as one of them is positive, one of those radicands is positive, we'll be okay. This next one here doesn't necessarily look like a complex number. It looks like a purely real number, which it is, but real numbers are also complex numbers. And if we wanted to kind of force that to be the case here, we could write this as 4 plus 0i to just really see that as a complex number in this form a plus bi. So this is just a reminder that all real numbers are complex numbers. It just happens that the complex portion, or the imaginary portion of the complex number has the 0 attached to it. So we don't typically write that, but this is just a reminder that real numbers are complex numbers, and we can write them like this if it does become helpful. All right, so next we'll hop into adding and subtracting complex numbers. What is nice here is that complex numbers play by all the rules that we're already familiar with from algebra. The approach here is to combine all the real and imaginary parts. So just like we've done in some other sections here, we're just combining all of the parts that are the same. So in this first example here, we can essentially just remove the parentheses. What truly is going on is we're distributing this positive or a positive 1 inside, which doesn't do a whole lot. But we can rewrite this as 3 minus 4i plus 2 plus 5i. And now I'm just looking to combine the real and imaginary parts. So the real parts here, we've got 3 and we've got positive 2. So that's going to give me positive 5. And then looking at the imaginary portions here, we've got negative 4i and positive 5i. Putting those together gives us just positive I. So here what we're doing is we're truly taking one complex number. To it, we're adding another complex number, and we're getting a new complex number. So the idea of adding the different parts and combining like terms is the process, but what we should get at the end is another complex number. All right, with the subtraction, there is a little bit of an extra step to remember. It's not that we can just take these parentheses off. We do need to distribute this negative here, just like we would with any other binomial. So now distributing this negative across is truly important for us to get the correct answer here. So as I rewrite this, we've got negative 5 plus 7i, and as I distribute that negative, we'll get plus 11, and we'll get minus 2i. Now that we've got that negative distributed into the second binomial there, we can go through and collect our like terms. So I'm looking for the real portions here. I've got negative 5 and positive 11, which gives me positive 6. And then going and combining the imaginary portions here, I've got positive 7i and negative 2i. If I combine those, I should get positive 5i. So there we go. We've subtracted two complex numbers, and we got a new complex number as a result. All right, next we're going to look at multiplying complex numbers. And again, complex numbers continue to play by all the rules that we're familiar with, but here we will include the fact that I squared is equal to negative 1. So if I just go back to our first slide here, I wrote that I is equal to the square root of negative 1. If I squared both sides here, then that would give me that I squared is equal to negative 1, which can sometimes be a more helpful form, and in this case, this will be a form that will be helpful to us. In this first example here, we might not need to use that, but these examples will pop up. Here we're just going to distribute this 4 inside to all of the terms, just like we would any other constant multiplied by a binomial. So what we're going to get here is 4 times 2 is 8, and 4 times 5 is 20, and let's not forget the I. So here we've got a real number, which is also a complex number, multiplied by another complex number, and we get yet a new complex number from that. So 8 plus 20i is the result of this one here. Now this next one, there's a little bit more going on because now there are two very complex looking complex numbers. They definitely look like complex numbers. Neither one of them is purely real is what I'm trying to say. So we will go through and we'll FOIL this out just like we would with any other two binomials, and we'll just keep in mind that if we get an I squared, then that is equal to negative 1. And I highly encourage you to write out those I squared terms and convert them to negative 1s. I was always guilty of trying to just skip to making that connection, and I'd end up missing a sign. So please work as carefully as you need to here. But if we're distributing the first terms here, we've got 4 times 2, which is going to give us 8. Distributing the 4 to the negative 5i is going to give us minus 20i. Distributing the 3i to the 2 is going to give us plus 6i. And here we can see that there are some purely imaginary parts that we can combine here in just a second. And then in our last step here, we're going to multiply the 3i by negative 5i, which is going to give us negative 15i squared. And this is where I was saying I encourage you to write that I squared thing. For me, it is insanely helpful to just work things out one step at a time. I don't mind using an extra step to do something if it means I get the right answer. Doing something more quickly and getting the wrong answer totally defeats the purpose. So now we'll go through and combine our real parts and our imaginary parts, make any substitutions that we need to. For now, I'm just going to leave 8 as 8. I'm going to combine this. I've got negative 20i plus 6i, which is going to give me negative 14i. And then I've got minus 15, and I'm going to rewrite that I squared as negative 1. And this just helps me keep all the signs consistent here. So now I've got 8 minus 14i. Negative 15 times negative 1 is going to give a positive 15. So here we've got positive 15. And now I can combine the real portions that are left here, and we will get 23 minus 14i. So again, we've taken two complex numbers, we've multiplied them together, and we've gotten a new complex number out of that. So before we talk about division of complex numbers, we need to introduce the complex conjugate, because this is going to be exactly what we need in order to do the division here. So the complex conjugate of a complex number is found by changing the sign of the imaginary part of the complex number. In general, a conjugate is if you have a binomial with either addition or subtraction in the middle, you will just change that from addition to subtraction or subtraction to addition, and that gives you the conjugate. Here we've got a complex conjugate, so we always put the imaginary part second in that binomial, so that is the portion that we will be changing the sign on. What is nice is when a complex number is, so I've got written here that if we have some complex number, a plus bi, then the conjugate will be a minus bi, changing that middle sign there. And what is nice is when a complex number is multiplied by its complex conjugate, we get a real number as a result. And what that is going to do with us is kind of in the background rationalize a denominator, even though we might not see that there is an irrational part there. Remember, we're taking the square root of -1, so there is kind of this irrational idea in the denominator there. It's also true that if you add a complex conjugate, or if you add complex conjugates together, you also get a real number. So there are some nice results from using the conjugates. So here, for these ones, we're just going to write down what the conjugates are. And then we'll use them in the next slide here to actually do the complex division. So if I'm looking for the conjugate, I didn't write any directions here, but find the complex conjugate, which means we're just going to change the sign on the imaginary portion of this complex number. So finding the complex conjugate of this means we're going to write 2 minus I square root of 5. I think in some of the examples we've put the I on the back end of the real number on that complex, on the imaginary part there. This is just a notational thing, because if I write 5 and I put my I there, is that underneath the square root? Is it not? It's kind of hard to tell. Like, is it there? Is it there? Those differences, or that difference would make a huge difference. So we just want to be careful there. And to do that, I'm putting the I in front of the square root, just so it's clear that it is not underneath the square root. But that is the complex conjugate of 2 plus I square root of 5 is 2 minus I square root of 5. Here we have -3/5 I, which may seem like a little bit weirder because there's no real part attached to it. This is purely imaginary. But, we could write this as 0 minus 3/5 I, and then maybe it's a little bit more clear that we are changing this middle term. You don't need to write this down. I think it's natural to just skip to the fact that this will be positive 3/5 I, but just kind of following my pattern here, I'm changing that middle term. And again, we don't need to write that 0 there, so what we'll get is just the 3/5 I. So there's the idea of complex conjugates, where we're just switching that middle term from positive to negative or negative to positive, and that will help us accomplish what we want in this next slide here, where we will be dividing complex numbers. So when we talked about rationalizing denominators, when we were talking about radicals, the idea was to use the conjugate of the denominator in order to rationalize the denominator. So that is what we're going to be doing here. And since multiplying a complex number by its conjugate does result in a real number, that's the approach that we're going to use here. And like I said, this approach is identical to rationalizing a binomial denominator. So what we're going to do is focus on the denominator here, and we're going to use its conjugate. And we're going to multiply this complex number by some stupid form of 1 that is built out of the complex conjugate of the denominator. So I'm going to write 4 plus I in my numerator and denominator. I'm going to multiply my original fraction by that, or my original division problem by that. And notice that this is just a big dumb 1. I like to make these big dumb ones. This won't change the value of anything. It will change the way that it looks, which is what we are after here. So let me just get rid of my 1. I'm going to put parentheses down because I'm going to need to FOIL a bunch of stuff out here. And we're going to need to make sure that we are multiplying everything by everything. So perhaps we'll focus, we'll just go kind of everything at every part here. I was going to maybe focus on the numerator and then do the denominator, but we'll just go and do everything kind of at once. So we'll start off with this 2 times 4, which will give us 8. Get some other colors ready here. Then we've got 2 times I, which is going to give us plus 2i. Then we're going to do 5i times 4, which is going to give us plus 20i. And then the last term here, we're going to have plus 5i times I, which is going to give us plus 5i squared. And we're going to remember that I squared is -1, and we can make that adjustment in just a step or two here. So let's go back and we'll look at the denominator. We can see that there's still some i's in the numerator, and that is fine. We are not trying to get rid of the i's in the numerator. We're trying to get rid of the i's in the denominator. So multiplying out the denominator here, we've got 4 times 4, which gives us 16. We're going to do 4 times I, which gives us plus 4i. And then we're going to do negative I times 4, which is negative 4i. And you might notice that those are going to cancel out. And this is the reason that we are using the complex conjugate, because this will make those middle terms cancel out. So we won't be surprised that that happens every time. In fact, if that doesn't happen, we're in trouble. And then we'll finish off with the negative I times positive I, which is negative I squared. So now we can go through and start combining like terms, combining the real parts and the imaginary parts, and at the same time we can convert these I squareds into negative ones. So we'll go through and simplify now. In the numerator, I've got 8. Combining these two terms here, it gives me plus 22i. And then just being very careful and converting this I squared into a -1, I'm going to have negative 5. So I didn't write out the negative that time, but now I know that that I squared says -1, and 5 times -1 will give us the -5. In the next step, I can combine that 8 and the 5, and we'll have our numerator simplified. Like I said, in the denominator here, those are going to cancel out, and that is the whole reason that we used the complex conjugate. We'll remember that I squared is -1. So now maybe being a little bit careful as I write this, this says 16 minus, there's still a minus in front of the I squared here. So 16 minus -1. So here I am trying to be extra careful to make sure I don't miss a sign here. So now looking at my real parts in the numerator, I have 8 minus 5, which will give me 3, plus 22i, all over, and now we've got 16 minus -1, which says 16 plus 1, which is 17. So here we have the denominator rationalized. We've gotten rid of the i's, which are square roots of -1, but like I've said in the past slides, when we were adding, subtracting, and multiplying, when we combine two complex numbers in that way, the result should be a complex number. If you add two complex numbers, you get a complex number. If you multiply two complex numbers, you get a complex number. We want to make sure our answer here also looks like a complex number, which means that we need a purely real portion and a purely imaginary portion. So we're just going to use the way that fractions add, but maybe in reverse to how we normally think about it, which means I'm going to pull this fraction apart over that addition in the numerator, and hopefully I can convince you that this is a legit thing to do. And I'm going to write 3 over 17 plus 22 over 17, and we'll make sure that we keep this I next to the 22 here, or next to that whole fraction. So maybe that step feels a little bit weird, pulling that fraction apart. Like, why can you do that? Normally when we think about adding fractions, we might think about going back the other way. And now we have a common denominator. You could just add the numerators together. So hopefully you can be convinced that these two do say the same thing, but now we're maturing in our mathematical abilities, and going the other way is something that is just as important to us. So like I mentioned, we divided two complex numbers, and our result is another complex number. All right, we'll finish off here by talking about powers of I. So we're just going to look at this column I've got on the left-hand side here, and we're going to see if we can't find a pattern and then use that to generalize as we go forward here. So we have I raised to the first power, which hopefully is clear that that is just I. Nothing too surprising there. The next one we have I squared, which we know from just our definition and things that we've already been doing that that is -1. Here, next we have I cubed. Okay, so now maybe we can start putting some things together, maybe use some property of exponents that we know. I could rewrite I cubed as I squared times I. So remember, if you have the same base, you can just add the exponents together. There's technically a 1 on that second I. 2 plus 1 gives us 3. But we also know from the last two that we just did that I squared is -1 and I is I. So this gives us -I. So as it turns out, I cubed is the same as -I. Okay, let's look at I to the 4th next. So different ways that we could think about this and how it might simplify. But one way I could do is by using I squared times I squared. Again, just properties of exponents, same base. You can add the exponents together and that would give us 4. And as we already know, I squared is -1. So what this says is -1 times -1, which is just +1. Let me write that a little better. My ones are getting weird. I don't know if that's better. I'll just go with one of those types of ones. Which is maybe kind of surprising or crazy that I to the 4th power gives us +1. But this is going to be what is going to make doing these examples and what we're going to be doing with these powers of I this is kind of the key here, that I to the 4th power is 1. And as it turns out, any multiple of 4 as a power of I will also give us 1. So we're going to kind of keep using that going forward here. We've got I to the 5th. I could write that as I to the 4th times I. And as we just discovered, I to the 4th is just 1. So this says 1 times I, which again is just I, which we started off with. We already have seen that one. Next here we've got I to the 6th. Oh, I could maybe write this as I to the 4th times I squared. We know I to the 4th is just 1. We know that I squared is -1. So here we've got -1, which we had here already. So you might be noticing the cyclical pattern that is starting to develop. I to the 7th, well, we can always write I to the 4th first. In fact, we're trying to almost find I to the 4th to turn them into just 1. When you multiply something by 1, nothing changes. What is left is an I cubed. 4 and 3 would give us 7 in those exponents there. We know that I to the 4th is just 1, and we know that I cubed is -I. And 1 times -I is just -I. And like we saw up here, we are continuing our pattern. So without even doing anything, we might guess that I to the 8th should also be 1. And as I mentioned before, any multiple of 4 should also give us 1 when it is a power on I. So to work this out explicitly, I could write I to the 4th times I to the 4th. And this would give me 1 times 1, which is just 1, which we saw again at I to the 4th. So hopefully now you are at least somewhat convinced that we have this cyclical pattern that goes I, -1, -I, 1. I, -1, -I, 1. So we can use this pattern to help simplify things like I to the 35th. So the way I'm going to think about this is splitting this apart into 2 powers of I, so that one of them is a multiple of 4, and I know that I to any multiple of 4 will give us 1, and then whatever needs to be left over on the other side will be left over on the other side, and we can simplify that just by using this pattern of I, -1, -I, and 1. So if I'm going to try and write I to the 35th here, well, let's see. I know that 4 will go into 35 8 times. So maybe I could write this as I to the 4th raised to the 8th. So this says I to the 32nd. This says I to the, well, maybe I'll write that first. So what I'm doing here is I'm forcing one of these exponents to be a multiple of 4, and we'll see maybe how that cleans up nice here in just a second. I was starting to kind of jump there, but let's do the in-between step. And then what is left over is this I cubed. So 32 plus 3 will give us the 35 that we started with. So now to like really work this out in brute detail here, I could write this as I to the 4th raised to the 8th power. This is just properties of exponents. 4 times 8 will give us 32. And we know that I cubed is negative I. So I could, in this next step, just maybe write times negative I. Well, I to the 4th is just 1. So what this says is 1 to the 8th power times negative I. Well, 1 to the 8th power is just 1. So let me scooch this work up here. Whoops. Give myself a little more space. And we end up here with just negative I as our result. So again, negative 1 to the 8th is just 1. 1 times negative I is negative I. So simplifying here to just negative I. We can do something similar on this next one. We have I to the 1,562, which is a big number. But if you recall, or maybe I'm just ask you to recall, that 100 is a multiple of 4, right? 4 times 25 is 100. So any multiple of 100 will also turn into 1. I know I'm kind of going deep into that logic there. But what I'm hopefully convincing you of is we only need to look at the last 2 digits of any power here to do that, because I could split, maybe to convince you a little further, this into I to the 1500 times I to the 62. And I to the 1500 is just 1. 1500 is a multiple of 4 because it is a multiple of 100. So this portion here is just 1, and I don't need to write that portion going forward because 1 times I to the 62 will still be I to the 62. Okay, so if I'm trying to write I and split it apart, so one power is a multiple of 4 and the other isn't, I believe that I can get this to go in 15 times. So 4 times 15, that'll give me 60. So 4 times 15 is 60. And I know that this just says 1, and 1 to the 15 is still just 1. So everything here on this left is just 1, and what is left over is, well, maybe I won't cross that out quite yet. And times I squared. So this says I to the 60 times I squared. As I started to say, this is just 1. So 1 to the 15th is just 1 times I squared, which is negative 1. So we're just using kind of this cyclical pattern. We're using things that we know about multiples of 4. We're using kind of remainders to get what would be left over here in order to simplify. So really what we're trying to do is turn one half of the split into 1, and then whatever is left over will go to one of these 4 in our cycle. Either I. So what I'm trying to say is the answer to all of these will either be I, negative 1, negative I, or positive 1. And we do that by just splitting it apart into one of the powers being a multiple of 4, and then whatever is left over will be left over, and that is how we will simplify that there. All right, and with that, we come to the end of this review lecture. Nothing left to do but practice, so good luck. Let me know if you want to see anything else here, and I'll see you in the next video.